Good morning, everyone. Today we're going to be doing 5.3, day 3. Our job is really just to review the things that we've learned over the last couple days in section 5.3. What we have here for you is a warm-up. I've given you the graph of the function f prime of x. So we're given the derivative of the function. From that, I'd like you to answer points A through E. Go ahead and pause the video. We'll go over the answers shortly. So for number 1, find and classify the critical points of f. Well, first thing we have to look at is what do we know about critical points? Critical points are where the derivative is equal to 0. Since we're looking at the graph of the derivative, I have two x-intercepts, so -2 and 3. And then my conclusion, if you look at what's happening at -2, the derivative goes from being negative to positive. So I go from having decreased slopes to increasing slopes. That means there's a relative minimum or a local minimum. And then my justification is, since f prime changes signs from negative to positive, that's why there's a local minimum at -2. Now at 3, my derivative is above the x-axis, and then it hits 0, and then it stays above the x-axis. So we have no sign change in f prime, which means there's neither a max nor a min. All right, number 2, find the inflection points of f. So what do we know about inflection points? Well, inflection points, we know a couple of things. That's where the derivative has a 0 slope and changes signs. Another way to state that is that's where the second derivative is equal to 0. So let's find that. Where is the slope of the derivative equal to 0? Right here, it looks about -0.5. So that would be the second derivative is equal to 0. And then right here at 3, you can see the second derivative is also equal to 0 because there's horizontal tangents there. Now, we also have to look for the sign change. So notice the slopes of f prime go from positive slopes to negative slopes. So I do have a sign change. And then here, my slopes go from being negative to positive, so I have a sign change in the second derivative as well. And that tells me that there are points of inflection at x equals -0.5 and x equals 3. All right, find the intervals where f is concave up. So what do we know about that? F is concave up anytime the second derivative is greater than 0. Well, second derivative being greater than 0, if I'm looking at the graph of f prime, that's where f prime is increasing. So I'm looking for positive slopes on this graph. Notice positive slopes going all the way up to this maximum. And then I have positive slopes from the minimum on. So we're going to say the interval from -infinity to -0.5 and from 3 to infinity. Right? That's where f prime is increasing. Find the intervals where we are concave down. So where is the original function concave down? That is going to be, notice when it was concave up, the second derivative had to be positive, while concave down, the second derivative is negative. To identify where the second derivative is negative, that's when f prime of x is decreasing. So where do I have decreasing slopes of f prime? Between the max and the min. So I would be decreasing on the interval from -0.5 to 3. And then finally, find the intervals where the original function f is increasing. Well, anytime the graph has positive slopes, I'm looking for when f prime of x is greater than 0. And notice, anything above the x-axis, and since this is the derivative, tells me that f prime is greater than 0. So when am I above the x-axis? From negative 2 to 3, coupled with the interval from 3 to infinity. All right. Keep in mind, the only way to learn math is to do math. Got to practice this stuff. If you're just watching the videos and not practicing it, you're relying a lot on your memory. And remember, we don't cover every single thing in class. You have to do some on your own to get the whole grasp and form the whole concept. All right. Now this part, you're going to probably have to pause and go through it. So let's talk about relationship between f, f prime, and f double prime. Now think about this. We're going to just look at slope. The slope of f is positive. So if the slope of f is positive, what do we know? And what about the slope of f being negative or the slope of f being 0? So what you'll probably want to do is, after we reveal the answer here, press pause and record that portion. And then you'll hit play and I'll tell you to pause it every so often. So if the slope of f is positive, think about that. It's going upwards, right? What do we know about the first derivative? The first derivative is greater than 0. The graph of f prime is above the x-axis. So that's when our slope is positive. Well, the slope of f is negative when the derivative is less than 0 and the graph is below the x-axis. And then the slope of f is 0 when the function has a derivative at some point. That's 0, that's where horizontal tangents occur. And the graph of f prime is on the x-axis. So what's written in purple is how this relates to the graph of f prime. Okay. Now, what if f is increasing? Right? What if the original function is increasing? That means the graph of f goes up. Right? So if f is increasing, that means there's a positive derivative. If the graph of f goes up, that means the graph of f prime is above the x-axis. Same thing with negative. If f of x is decreasing, then we know that the graph of the original function is going down, and we know that the derivative of that graph is going to be below the x-axis. It'll be negative. If f is 0, if the slope of f is 0, then f of c has a horizontal tangent, and you know that the graph of the original function is flat. Right? So what if we go backwards? What if we were looking at the original function and I saw a horizontal tangent? My conclusion is the graph of f prime would be 0. It would be on the x-axis of the graph of the derivative. Okay. Now, what do we know about f double prime, concavity? So if I know that the slope of f is positive, I can't really make any conclusion about the graph of the second derivative because we don't have any information. And that same thing with the second derivative, knowing the slope of f is negative. Okay. But what about if the slope is 0? Well, we have to kind of do a little bit more investigating here. If the slope of f is 0, and we know all this is true, is that an extreme point? Is c a critical point or a stationary point? Is it a maximum or a minimum? Well, what we need to do then is we need to look at the graph of f prime and see, does it change signs from positive to negative or negative to positive? And that's the graph. If possible, we look at the graph of f prime to see if it crosses the x-axis. Right? That's basically our first derivative test right there. Right? Now we do have a connection. The second derivative test says that if f prime equals 0 and it changes signs from positive to negative, right? F prime changes from positive to negative, then f of c is the highest point on the hill, meaning it's a local maximum for sure. It might be the absolute max, but we don't know that officially. But we know for sure that a local or relative maximum would occur. The second derivative test, we would conclude then that the concavity at that point of the original function would be negative, because the only way that we could have a maximum is if I'm concave down. Okay. Well, what if we have a minimum, right? What if the original function has a minimum? What do we know about the first derivative? The first derivative is 0, and it changes signs from negative to positive. So f prime changes from negative to positive. That would tell us that the original point at that point is the lowest point in the valley. So it would be a local minimum. But the second derivative test would inform us that the concavity at that point, the only way we're going to get a minimum is if the graph opened upwards and had a concave up portion. So this is basically another way to think of what we talked about before, the first derivative test and the second derivative test, and how f, f prime, and f double prime are all related. Okay. There's another way to view this with concavity. What if we know that the original function is concave up? Or what if we know the original function is concave down? Well, this is just a nice way to form your thinking. So if the original function is concave up, I know for sure the second derivative is positive. Right? And on the graph of f prime, that would be f double prime, that would be the points would be above the x-axis. F is concave down when the second derivative is negative. And on the graph of f double prime, all the points would lie below the x-axis. But how does that relate to the first derivative, right? So if f is concave up, right, that means my function's derivative, so f prime is increasing. And on the graph of f prime, that means those points would be going up. If f is concave down, then f prime is decreasing. And on f prime graph, that means the points would be going downward. So think positive slopes to negative slopes. Well, what does that mean about the original function? If these were all true, f of x opens upwards for concave up. If it's concave down, f of x opens downward. So notice how we kind of link some things together here. Some students like this. If f double prime is positive, that means that f prime is increasing, which means the original function graph of f is concave up, which would produce a minimum point. Oh, I revealed it too soon. But if f double prime, forgot tick marks here. If f double prime is negative, you know that the first derivative is decreasing. And if the first derivative is decreasing, then we're going to be concave down. And there's going to be a maximum point, a local maximum point at that critical point. All right. Now, f has a point of inflection. So what happens when we have a change in concavity? Well, a couple things have to be true. F double prime at the critical value has to equal 0, and it must cross the x-axis, meaning it has to have a sign change. The second derivative must have a sign change in order to have a point of inflection. F prime of c is a local max or a min, so we can conclude that when there's a change in concavity, it changes at a local min or max of the derivative, and then the original function at that point has a max or a min slope, right? Meaning the derivative is a max or a min, and concavity changes. So we've kind of talked about all that. All of this is just a piece to put it all together. So if you need to go back in the video and pause anything to write it down, please do so. Otherwise, look at the posted notes on Schoology, and you'll get all of this in one nice document. Let's actually apply it now. So here is the graph of f double prime. I'd like you to answer A through D. Go ahead and pause the video, and we'll go over the answers shortly. All right, so big thing to keep in mind, we're looking at the graph of the second derivative here. So how can we find critical points of f? Well, in this case, it's not possible. It's hard to go backwards from the graph of the second derivative looking at critical points because we're not really sure yet how that would play out. But we can look for points of inflection, right? Points of inflection are the spots where the derivative, the second derivative, has to equal 0, and there has to be a sign change. So let's see. This is the graph of the second derivative. 1, 2, 3, 4, 5, 6. Right here at -6, notice we have a 0 second derivative, and we go from being negative to positive. So there is a sign change there, which proves we have an inflection point. Over here at -2, we go from positive to negative second derivatives. And then 1, 2, 3. Here we have the same thing. We go from being negative second derivative to positive second derivative. So we have a sign change there as well. The next piece, we're looking for intervals that are concave up. Well, remember what concave up is. Concave up is when the second derivative is greater than 0. This is the graph of the second derivative. So when are we above the x-axis? Anytime the values are positive, right? So this would represent concave up of the original function. So I know from -6 to -2, I'm above the x-axis. And then again from -3 on. And where are we concave down? Concave down when the second derivative is negative, which is when the graphs of the second derivative are below the x-axis. So I'll just put concave down for that part. And that gives us the interval from -infinity to -6, and the interval between 2 and 3. And actually, I think I mistakenly wrote -3 right here. It's an actual +3. I misread my sign change. So that should be a +3. All right, so you're going to get a worksheet here today. Go ahead and take a look at it. And what we'd like you to do is keep in mind the relationship between f, f prime, and f double prime. The answers are on Schoology, so check your work as you go. Give yourself some confidence of how you're doing. Good luck. Adios.